All right, hello geometry. Um, Today we're covering a different unit. Initially, we were going to cover over um, volume and area and surface area, but I actually, after a little consideration, I actually determined it better for us to jump to our probability unit and cover that before our state test, and we will come back to volume, surface area, things like that, and we'll have a little bit more review on that before the state test. But I think covering probability is probably the better solution for the amount of time that we have left before our state test. So we're going to start off with talking about today just sort of basic probability. A lot of the stuff you actually saw in seventh grade when you covered probability then. Um, but today we're going to cover basic probability. You should have just finished your spinner activity where you were spinning a bunch of spinners and sort of looking at what was more likely about those spinners or how we could use those spinners to estimate certain things. So starting off with what is probability? So probability is essentially the mathematical definition that we have is the likelihood. Oh, I need to change my size of font. I'm sorry. So the likelihood of a certain event happening, whatever that event might be. So probability is the likelihood of a certain event happening. So the likelihood of me flipping a coin and it landing on heads, the likelihood of me rolling this dice and it landing on a six, the likelihood of um, going outside and it raining. Those are all different things of probability. So how do we determine probability? Well, we need two things in order for us to be able to calculate probability. The first thing is the total number of outcomes. And then the second thing is the desired number of outcomes. So in order to calculate probability, we look at the probability of an event. So this is the notation that we use when writing probability. So this we do P parentheses. So the P stands for probability, obviously, and then the parentheses, inside the parentheses we always put what the event is that we are talking about. So P parentheses event. So if you're looking for the probability of flipping a coin and landing on heads, you could put like P, the probability of heads, or you could put the probability of tails in here. You could put the probability of raining. This is just a shorthand notation for us to say the probability of this event is equal to, and we always need to do, it's always going to be a fraction. It's desired outcome divided by total outcomes. The probability is always calculated by desired outcomes divided by total outcomes. Now, desired means just the number of outcomes that you want. So if we're flipping a coin and having land on heads, we have essentially one outcome. The head side is our desired outcome. That is the outcome that we want. While there are two total outcomes, the number of total outcomes are two. There's the coin can land on heads, or the coin can land on tails. Those are the number of total outcomes, while my desired outcome is it landing on heads. So my probability of a coin landing on heads would be 1 out of 2. And that's how we calculate probability. So we're going to look at a lot of different examples of this today. It's always desired outcome divided by total outcome. So that's always what we'll want to remember for calculating probability. So when we're dealing with probability, it turns into a fraction. Now this fraction, we either can leave the probability as a fraction, or we can turn it into a decimal. Now this fraction is always going to be between the probability, or always going to be between 0 and 1. We can never get past 0. We can never have or get past 1. So our probability will always be between the numbers of 0 and 1. So if you're calculating the probability of an event and it's not between 0 or 1, then we messed up somewhere in the problem. We'll have to go back and change something. Now, when something is 0, that means it is impossible to happen. There is 0 probability or 0 chance of it happening. While something is 1, You can also think of this like percentage. One would be 100%. So it's almost, or it's certain, it's has to happen. There is only the chance for it to occur. And then everything in between that is going to be there is a chance to occur, there also isn't a chance. 0.5 or 50-50 would be equally likely to occur or equally likely not to occur. Once we get less than 0.5, it becomes less likely to occur. When we get greater than 0.5, it's more likely to occur. So the closer you are to 1, the higher likelihood it is to occur. The closer you are to 0, the less likely it is to occur. But once again, you will always be between 0 and 1. So a quality control inspector samples 500 computer monitors and finds a defect in 3 of them. What is the experimental probability that a randomly selected monitor will have a defect? Now, experimental probability, we have 2 types of probability we're talking about today. Experimental probability is our first one. So experimental probability means that looking at data or looking at a result or after performing some sort of experiment or observation, you have data that tells you information you can use to find probability. So we are looking for what is the experimental probability that a randomly selected monitor will have a defect. Well, we know probability. We need to figure out, so what's the event that we're looking for? The probability is that a monitor will have a defect. So we're looking for the probability of a defect. That's going to be our event. And we know it's desired outcomes divided by total outcomes. So looking at the data we were given, what desired outcomes do we want? Well, we're looking for defects. So how many desired outcomes do we have? How many defects do we have? And we were told that we had 3 defects. So our number of desired outcomes is 3. After that, we have to look at the number of total outcomes. So how many total computers were sampled? Well, we sampled a total of 500 computers. So we're going to do 3 divided by 500, and that's going to be our fraction. We can then divide this and turn this into a decimal, and that will be our probability. So 3 divided by 500 gives us 0.006. Now this is very close to 0, so this is a very unlikely chance of it occurring. It's a very small chance, but that would be our experimental probability. Now, if the company manufactures 15,240 monitors in a month, how many are likely to have a defect? So once we have the experimental probability, we can use this to predict future events by calculating that probability and seeing the total number of chances for it to occur. We can multiply those together, and that will give us our probability or predictive probability. So if the company has 15,240, while 0.6% essentially of those computers can have a defect, we can figure out what is this number of 15,240, and that will tell us our total number of computers that might have a defect. So we're going to take our probability, 0.006, and we are going to multiply that by 15,240, our total number of computers that are being manufactured in a month, and that will tell us how many defects we have. So we'll just multiply the probability by our number, and that will give us our answer, which is 91.44. Now, once again, obviously you're not going to have 0.44 of a computer being a defect, but this is just a prediction. So you should have roughly about 91 of your computers should have defects. Now, it doesn't say it's going to be. It's not automatically that. Probability is never, it's not the law, but it helps us predict events. So just because the probability of a coin landing on heads is 50-50 doesn't mean it's always going to, one half of it is always going to land on heads, half of it's always going to land on tails. Probability is a predictive event. It doesn't automatically tell you it has to happen. Just because something has a 0.000000 chance of happening doesn't mean it's impossible. It can still happen. And if given enough time, it will happen. So it doesn't mean there's automatically going to be 91 of those computers are going to be defective. It's possible that all of them work perfectly fine, but it means roughly 91 of those computers should be defective based off our experimental probability. A park has 58 or 538 trees. You choose 40 at random and determine that 25 trees are maple trees. What is the experimental probability that a tree chosen at random is a maple tree? So once again, same idea. Actually, if you want to pause the video here, you can take a moment and see if you can solve this one for yourself. I think you could do it pretty easily. I'll assume you pause the video and are coming back now. So when we're trying to find the experimental probability, we just have to think what is the desired outcomes divided by total outcomes. So our probability of having a maple tree is going to be, okay, so we chose 40 trees at random. So we tested 40 trees and 25 are maple trees. So we got 25 desired outcomes out of 40 total outcomes that we looked at. The 25 out of 40 would be our probability. So we could divide that to get our decimal, and that turns out to be 0.625. So 0.625 is our probability of getting a maple tree. Now, if we wanted to figure out how many trees in the park should be maple trees, we can once again use that decimal 0.625 and multiply it by the total number of trees in the park, which is 538. And this should tell us roughly about how many trees in that park should be maple trees, assuming we took a good sample of all of the trees in the park. So we'll do 0.0625 times by 538 and multiply those together, and we got 336.25. So roughly about 336.25 trees in the park should be maple. Now, once again, it doesn't mean it is automatically maple, but it should be based off our example that we've done so far. All right, moving on. Theoretical probability is our second type of probability that we talk about. So we have experimental probability and theoretical probability. Well, so experimental probability was based off of observations or tests or getting data. Theoretical probability is based off what we know about the event without having to perform any tests or observations. So when we're doing theoretical probability, we're not actually flipping a number of coins or rolling a bunch of dice or counting trees or inspecting computers. This is just based off what we know should happen, based off what we know about the event. All right, so for example, what is the theoretical probability of drawing a queen from a deck of cards? So it's just a normal deck of cards. We just have to use it, or we're not actually pulling a bunch of queens out of a card and seeing how many times we get a queen. We are just doing it based off what we know about the event. So our probability of getting a queen is equal to our desired outcome divided by total outcome. So what is the desired outcome? So the desired outcome is getting a queen. So how many queens are there in a deck of cards? Whether there's queen of hearts, there's a queen of spades, there's queen of clubs, there's queen of diamonds. So there's 4 queens, one of each suit, in a deck of cards. Well, how many total outcomes are there? How many total cards are there in a deck of cards? Well, there's 52. There's an ace through king of all 4 suits, which gives us 52 total cards. So 4 out of 52 is going to be our probability. So if we can divide that, we would get 0. It's not typing for me. 0.769 is going to be our probability, and there's a little bit of decimal in there, and we can round it to nearest thousandth place if we need it. It doesn't necessarily matter exactly what decimal we go to, but our probability of getting a queen is 4 out of 52, which is 0.0769. So there's a sorry, I missed a 0 in there. I was like, that's a little high of a chance. There we go. That's a little bit lower. Keep to our 0.077 is our decimal getting a queen. Sorry. So that's our theoretical probability. Once again, we didn't draw a bunch of queens from a deck of cards to test this. We just did it based off of our knowledge of a deck of cards. So what is the theoretical probability of rolling a number and getting a number greater than 4 on a standard dice? So when we think about it, it's theoretical probability once again. So rolling a bunch of number, or rolling a number greater than 4. So our probability is getting a number that is greater than 4. So a standard dice has 6 sides. We think what numbers are greater than 4? Well, 5 and 6 are greater than 4, so our desired outcomes would be either a 5 or a 6. So there are 2 desired outcomes out of my 6 total outcomes on my dice. So if I divide 2 by 6, That gives me 0.33 repeating. So I can just do 0.33 as my decimal. So this is the theoretical probability of rolling a number greater than 6. Now let's say I rolled a dice 12 times and got these results. What is the experimental probability of rolling a number greater than 4? So this is the actual probability. This is the experimental probability. I actually performed an observation. Now what's my probability? Our probability of getting a number greater than 4. Well, once again, we have our desired outcomes. Our desired outcomes is a 5 or a 6. Those are the two numbers that are greater than 4. If I look at the frequency of when those are rolled, I rolled a 5 3 times, I rolled a 6 2 times. So I had 5 out of 12 total rolls, because there's 12 total rolls that we did. So my experimental probability was 5 out of 12, which doesn't exactly match our theoretical probability. Once again, experimental probability and theoretical probability aren't always going to match. Probability isn't like always going to happen. Just because the chance of it was 0.33 didn't mean it always happened 0.33 of the time. Now, assuming I kept rolling and rolling and rolling and rolling and rolling, the more times it happens, the closer likelihood we should get to that theoretical probability. But the experimental probability and theoretical probability shouldn't always necessarily match up. Sometimes it will, sometimes it won't. But that's our difference between experimental and theoretical probability. So using these frequency tables to calculate experimental probability is another thing that we do quite frequently. All right, last thing we're talking about, the complement. So the complement of an event consists of all the outcomes in which the event does not happen. So it's essentially saying when does it, or what is the opposite of this event. So the complement is always the opposite. So for example, let's say what is the probability of rolling less than 3 on a standard dice? So if we think about it, probability our number we roll is less than 3. Well, what numbers are less than 3 on a standard dice? Well, our numbers are 1 and 2. So once again, it's a 2 out of 6 chance, similar to like what we did with the greater than 4, the 0.33. So that's our theoretical probability. So the complement of this event would be the opposite of this happening. Sometimes you see this written with like a little c. So we would be calculating the probability of getting a number that is less than 3. Sometimes we put a little c in the top right of that. That tells us this is the complement of our event that we're calculating, or the opposite. So we just have to think, what is the opposite of this event? So this would be equivalent to the same as the probability of getting a number. Well, the opposite of less than 3 is a number that is greater than 2 is the opposite of less than 3. So what numbers are greater than 2 on our 6-sided dice? Well, there are 4 of them. There's 3, 4, 5, and 6, which would give us 0.67. Now, if we think about it, the opposite of an event and the complement, whenever you're calculating the probability, all of the total outcomes should come together to equal 1. So if you take all the probability of a bunch of different events that can happen, if you add all those probabilities together, it should always, always, always come together to equal 1 or 100%. So an event and its complement, if you add them together, should always equal 100, because you have the event, you have the opposite of the event, which is all the other outcomes of it happen or of it not happening. So it's the probability of something happening and the probability of something not happening together should always equal 1. So remember, whenever you calculate the probability of all of the events entirely together of a certain group, if you add all those events together, it should be 100%, or 1 should always be added together in the end. So that's our probability. That's where we're going to cut it off for today. You should have a couple little activities or practices after this. Let me know if you have any questions. Have a great rest of your day.